Okay, hello class. Today we're going to be looking at different distributions and when to pick the right one. And so I'm going to start with this fun kind of question about deal or no deal. And so deal or no deal will be one of our examples of distributions, one that we've already seen. And it also kind of shows that like there is, back to the big idea, just this idea of like using probability to make decisions. Expected value is going to be a big part of that, but really what we're doing here is making a decision about which probability to pick. So as a warm-up, you've got a deck of cards. If you're conducting a game that uses 52 cards, like how are you going to do it so that it's a binomial, hypergeometric, or uniform? So how do you think about this? The binomial and hypergeometric examples actually came up in the lesson 2 and lesson 3, and so binomial, it doesn't really work that well, but if you picked like 3 or 4 cards and you put the card back in every time, then it would be binomial. The slight change for hypergeometric is if you pick 3 or 4 cards, you just put them in your hand, and so that's the more natural thing to do. But notice how you're picking like more than one card. For uniform means that the probabilities are all the same, and so you'd actually have to pick just one card. And so if you just picked one card, what's the probability that it's a diamond, heart, spade, or club, and they're all 1 out of 4. So today the big thing that we're working on is how to decide which distribution to pick, and then like applying that distribution or to solve the problem. So, but also like big thing is like being able to differentiate the reasons why we would use binomial or hypergeometric, because those are the ones that are going to be very similar, say in a situation like this. So the first example came from that list. A study reports 5% of adults are afraid to be home alone at night. And I think I got this from CBC News. I have a couple other sources in the summer of 2017. So you could actually search this CBC News, and then if you're interested in this study. But if people are randomly selected, calculate the following. The probability that one person's afraid to be home alone at night. So you realize that when you see this question, unlike in a deck of cards where you're choosing from like a 52, like you would really need that total to choose from if you want to use the hypergeometric formula. But if you have 5% and the 5% is never changing, then that's where you're going to use the binomial formula. And so the binomial formula would look like this. We could do anything from 0 to 20. And in fact, in the second question, we'll do 3 to 20. But the 5% and the 95% don't change. They're like the 5% chance of the first person, 95% chance for the next 19 people, and then 20 choose 1 cases. So there's 20 ways that you can pick one person from a group of 20 to be afraid. The at least 3, so you can try the at least 3. You can do it on a spreadsheet as well, but really like you don't want to do 3, 4, 5, 6, 7, and so there's a bunch of cases. It's far easier to do just the 0, 1, 2 case. So this is saying probability you're bigger than 3 and equal to is the same as 1 minus the probability you're less than or equal to 2. And so the 0 is here. This is the one we already calculated that, and this is the probability of 2. And these numbers just come from this exact same formula where we changed the number 1 and the number 19, and this one as well. And the expected number, you don't need a whole chart. If it's binomial, we just take the 5% of 20 and we get one person. So there's an example of binomial. If you tried hypergeometric, you wouldn't have a total you're picking from. So on the bottom, like it'd be weird to say like out of how many you're choosing 20, because like you don't have a total that you're picking from. Here you're selecting 5 cards from 52. So this is like one of our base hypergeometric or combination cases. X is the number of hearts you get, so you could get anywhere from 0 hearts to 5 hearts. And the probability of 3 or more would be the probability 3 plus the probability 4 plus the probability 5. And I don't show it here, but you can use the hypergeometric formula to verify that you're able to get 8%, 1%, and 0.5. And it's just a matter of using those 2 groups on top. So to the 13 hearts, we've got to choose 3 of them. And out of 39 other cards, we're choosing 2 of them, and we're dividing by 52, choose 5. So 13 choose 3 times 39 choose 2 divided by 52 choose 5. And you do that for 3, 4, and 5, and it's 9.28%. And then the expected number of hearts, so I always say it this way, like if you're drawing 4 cards, how many hearts do you expect? If you're drawing 8 cards, how many hearts do you expect? If you're drawing 2 cards, how many hearts do you expect? It just has to be in the same proportion. So if you're drawing 5 cards, we expect 1 1/4 of them to be hearts. This formula, I don't love the formula. It's just basically saying 13 out of 52, which is the quarter of 5. And it's very similar to the binomial formula. It's basically 25% of 5. Describing what this number means, it just means like we expect 1.25. So we're never going to get that, but maybe like one time we're going to get 1 heart. Sorry, 3 times maybe we'll get 1 heart, and 1 time we'll get 2 hearts. So we're more likely to get 1 heart than 2. And here's now just note, I did make up this number 2%. So this is, I had to put a number in there, and it wasn't in the article. It might be now, and so like you can check the article if you'd like, but I just use the number 2%. So this is like if you're infected, or if you say that you use street drugs, potentially you have a certain % chance that you have fentanyl in your body. And so that's kind of a scary thought. It's basically dodge a Mack truck then, because if you had fentanyl in that street drug you took and you didn't know that, then it's very, very dangerous. And we've seen that in the media. Recording this video, we've seen that in the media fairly often. And so there were no probabilities quoted in the article, but so I used some numbers to create the example. So if you have 100 people, what's the probability that 2 or more of those people will test positive? We're not going to do the cases 2, 3, 4 all the way to 100 again. We can use the indirect method. And so we're going to use the probability that we're less than or equal to 1. So just subtract the probability of 0 and probability 1 from 100%. So you should get 60%. I'd invite you to recreate that calculation on your own, but you should get 60%. Now this is a binomial distribution because we're not drawing from a population. We don't have that number. We just know that the percentage doesn't change. It stays 2%. And then the expected value, we don't have to use that big chart. We have a formula for it. It's just 2% of 100, which is 2. And I put the source for this one. This number is actually really small. It should be bigger, but we're going to say that out of any 30 car accidents, then authorities are saying that 1 in 4 are caused by texting and driving. So authorities want to see what's going to happen out of every 30. So a group of 30, if 30 car accidents happen, how many of them are going to be caused? What's the probability that certain number are going to be caused by texting and driving? So. But the study's saying it's 1 in 4, so we're going to see based on that probability, what is it going to be? And so we talked about this one before, and it is actually a binomial. Again, we're taking 30 as our sample. The wording's just a bit different. We're taking 30, but we're not taking it out of 1,000. So if you knew how many there were in the study. And actually, this study, it's not the exact same one. It gives numbers, but I actually note that that 1 in 4 is really low. It's probably more like 2 in 4 are caused by texting and driving now. Probably that 10 or more accidents are caused by texting and driving. That question I would really use a spreadsheet for. It's a binomial. You have to take the cases from 10, 11, 12 all the way to 30, or subtract the cases 0 all the way to 9 from 1. But I would do that in a spreadsheet with a binomial. 8 to 10 is a bit easier to do by hand, so 8, 9, and 10. And so again, using the binomial formula, 30 choose 8, 30 choose 9, 30 choose 10, and then the probability would be 0.25 and 0.75. And the expected number is 25% of 30, which is 7.5. The last one's deal or no deal. And I think I blacked this out before, and then I decided to like keep it. So I'm pretty sure the offer was $59,000. So in this game, like you have a chance that one of these is your prize at this point in the game, and so the banker's offering you some money, so 59 grand, to just like have you quit the game, and so he can keep his money. So are you going to take it or not? Now there's a chance you have $1, but there's a chance you have 500,000. So you can imagine you got to figure it out. The way you would do a question like this is you're really just doing the expected value, but this is a uniform. You're only taking one case. So you have a 1 in, I think, 13 chance that your prize is any of these prizes. And so for uniform expected value, you can do the chart, but it's really just the average of the 13 prizes. And if that's higher than 59,000, I wouldn't take the deal. If it's lower, then he's offering you a pretty good deal. So a couple things you're looking for here is binomial is independent. So every trial is independent. That probability doesn't change. So heads, coin flip doesn't change. 2% of product's defective. It's always defective. It doesn't change. For hypergeometric, you're dependent. So like as we pick items, like we're losing cards and we're losing people. So the probability is going to change. And so then you use combinations. Picking committee people. The other thing you can look at is limited versus unlimited trials. So technically, in binomial, because the probabilities always stays the same, you could choose the sample that you're choosing. Like we had some examples here, like the 30 car accidents. You could have done that as 100 car accidents. There's no real limit to the trials possible. In hypergeometric, there's a limit. So you have like a population you're drawing from. You can't take more than that. So if you only had a population of 30 people, the most you can take is 30. 52 cards, you can't just keep drawing cards if you're not replacing them. In binomial, and you're replacing the card, you could draw the card as many times as you want and play any kind of game with that. And so that's what the limited versus unlimited means. It's just something I came up with to kind of help you understand and just help to kind of think about when you have a total population that you're dealing with, that's a hypergeometric. Okay, and so a question like this you can look at trying to change the scenario. So this is hypergeometric. We could change it to binomial if it was if we didn't know how many tickets she had. Like we just know it's a 40% of blue and 60% of green, and she's going to give you 2. And potentially she has a lot of tickets, it maybe doesn't matter. So it's just 40% are blue and 60% are green. And even though like there is a limit to the number of tickets she could have, you don't know that. So you don't have that information, like how many tickets she actually has. And then like 40% of the music you listen to is Canadian artists. So again, this is a binomial situation. To change it to hypergeometric, you just have to say like, you have 100 songs and 40 of them that you listen to are Canadian. And so that's like the